All right, so we are here to talk about ELF, the ABI, and computational privilege. We're, wait, what happened to the, oh, okay. So why don't you introduce yourself?
I'm Prashant, and I'm a PhD student at Dartmouth. I work with Sergey Bratis, and I work on language theoretic security and ELF.
And I'm Bex. I'm a senior security researcher at NARF Industries, and I studied with Sergey Bratis in the Dartmouth Trust Lab previously. I recently graduated, and my specialties are ELF, bootloaders. I've been working on dynamic analysis. I try to do defensive research, and yeah, why are we here? We kind of want to tell a story about a project that our lab has been working on for a while called ELFbac, which we think has this nice way of defining and enforcing the intent of a programmer. And we found that it has a really nice, it nicely works with Spectre and acts as a nice mitigation. And it's sort of tangential to all the other mitigations that are there for Spectre variant 1, and Prashant will talk about that later. But with the ELFbac, we see that the ABI, the application binary interface, really merge it really well, is a good boundary and a good mechanism to capture programmer intent. Before we get into this, though, I want to start with a story. One day in the live, freeze, or die state, I made my way through, 10 feet of snow, uphill both ways, to the Dartmouth Trust Lab. I wanted to go for a visit, and when I got there, I got the traditional Trust Lab greeting. Bex, we're surprised to see you here. They're so nice to me. And so I respond, and I may have been there for free food. I forget. It was, about January after the Spectre and Meltdown was publicly released. So they tell me, lately we've been thinking about Spectre. Yeah, so has everyone. This is January of the month in which all these details were released. Yeah, okay. And maybe Sergey kind of goes off on a tangent about Russia. Well, we're thinking ELFbac may naturally mitigate Spectre v1. And we'll kind of go through and talk about what ELFbac is and what Spectre variant 1 is. But this is sort of the conversation that was going on. And I'm like, huh? Like, this doesn't make sense to me. Let's think about this a little. So, several months later, we're kind of trying to get this working, and well, it seems to work. Yeah, I was wrong to doubt, but we also ran some more experiments to just think, to look at timing, try to get an understanding of these micro-architectural artifacts that we're measuring that are part of Spectre. And so we did. So how did we get here now? Well, long ago, 2013, in the galaxy far, far away, the Milky Way, people wrote really bad software, and I guess they still do. And so in the far reaches of northern Appalachia, we thought up ELFbac. And this is sort of our lab project, and basically the idea was that ELF files, which are the executable library binary file format of Linux and a lot of similar systems, they retain a lot of semantically interesting metadata that are subsequently ignored by the runtime. And so, yeah, that makes sense. And some of us didn't know what ELF was, but we decided to look at it, the lab, and, well, go on, Sergey. Software by design is split into parts. The libraries, compilation units, functions, object files kind of match this. And in other words, these parts are semantically related to code and data. So you'll see libraries will be the crypto library, you'll see libraries for particular functions, but also you'll write files as part of the program. This implements the linked list, this implements database search, and so forth. And information about these different parts are expressed in ELF files. They're stored in separate and distinct ELF sections at during some points of the compilation process and eventually brought together. And these metadata are for compilers, static linkers, and the binary toolchain, and are wastefully disregarded during runtime. But if we use them, the intent can be, there can be a policy that enforces intent at runtime, even if the software is compromised, because we can start actually reflecting this intent of what should be accessing what through what we ended up doing was page table permissions. And we decided to do it in sort of a runtime state dependent. So if we know the software is running in trying to work with crypto, well, then it can access the keys. But if it's processing user input, it shouldn't be. And we can reflect this on this ABI level using page table permissions as the software executes. Now, imagine a world where sections of an ELF are types and linking is a policy that works across these types. The runtime loader constructs an address space based on these ELF metadata. And I have a little like mock-up, and each different color is a different section. Some of them are libraries, some of them are the main executable. But it's, you know, the red is executable, the yellow is read-only, and the green is read-write. And maybe we're looking at like the web server, or maybe it has like a libpng in there. Well, a vulnerability in a library in the overall executable can propagate and make the entire executable vulnerable. And when sections are policy objects, the policy can be explicitly put in to prevent, you know, say libpng from leaking any key material. And this is what we call ELFbac, an ABI-based intra-policy sort of memory access control list. And we'll discuss the implementation later. But I've been saying ABI a lot, and just like so we're all on the same page, this is, you know, an example ABI that for, what's it? And so x80, 64-bit, x86, and it actually defines how different components of binary objects, such as libraries and executables, interact with each other, and these standards, and also, it also talks about how variable length arguments are taken in functions and different data types, but it really defines a lot of what ELF files are based out of. And we think this is a nice granularity to work on. Perhaps just right. I mean, it's really hard to compare ELFbac against, say, memory protections and SE Linux. It's like comparing apples to oranges. I mean, they're both sweet, but there's definitely tangential things that are hard to compare. But if we're looking at how memory protections are done generally with kernels, it's read, write, execute different parts of memory. And it's sort of fixed during the runtime. More or less, it can be changed, but that's sort of an explicit decision. With ELFbac, permissions can be dependent on these sections that we define at compilation time. The developer can say, this contains key material, this contains buffers for an image that we're processing, and this is the code that processes key material, and this is the code that processes untrusted input. And during the execution phase, we can start having like known entry points into these different phases. I am processing input, I am processing key material. And SE Linux has this very small granularity of system calls, individual files that need labels, and it can be kind of hard to work with. And what Sergey likes to do, who is our leader of our lab, is show that the ABI is sort of this sweet spot between different kind of layers in what we think about in policy. So like the security relevance, the tractability, and also just like how much effort it takes to build this policy. And remember, if it looks like a duck, quacks like a duck, but needs batteries, you probably have the wrong abstraction. And so maybe just having like memory read, write, execute is not enough, and maybe we should really rethink the way we enforce policy within the executing process. In ELFbac, I mean, it doesn't protect against all attacks. It's not there to be your buffer overflow. However, or to prevent buffer overflows. However, if there is one, contained in a certain phase and not necessarily be propagated into phases of execution where it's processing key material. And what is nice about it is it can capture and enforce developers' intent on these layers of boundaries of libraries and so forth and the main application. So the moral of the story is that all libraries and sections of memory can be trusted equally, yet that's what the current state of things are. And when an executable is loaded, all the libraries are in the same address space and everything is treated the same in terms of policy. ELFbac allows us to enforce these intra-process access controls at the ABI granularity, so processes don't have to treat their entire address space as equal. So to try to make this a little more real, you can think of a case study of some software that fetches and decompresses image PNG files over SSL. So you can think of the different phases of execution it goes through, and you can also think about the regions of memory that it accesses during this flow, during each phase of execution. So initially, the SSL will be initialized, and then in that it will read its keys, and then it'll perform some SSL again, and it'll probably read the keys again at that point. And then suddenly, it's invoking libpng to process this image for some reason, and that's suddenly working with an input buffer. And then there might be some more application logic that is working on the output of libpng. And each data code segment that we pointed out here, the SSL initialization, libpng, the keys, and so forth, can be put in their own little sections in the ELF file without too much trouble. It's sort of part of what ELF does, is add little markers to different sections inside the file that tell the loader what is code, what is data, but we will add a little more information so we can have. So if we're using both openSSL and libpng, what if to make this example deeper? We'd be loading libpng into address space, and you don't really know how this loading and how libpng will affect, like if there is a weird effect with libpng, we need to understand that. And especially in the current model where everything is sort of treated equally in the address space. And you need to kind of understand how this affects our mental model. So if the attack is this PNG file, it may end with the current model overwriting some critical data. And from that, you might end up having the execution do something different or leak priorities. And so with the separating permissions for each section, suddenly the keys are not readable by libpng, and libSSL will only access its own code, its own data. And you will explicitly define places where the two can intersect. Well, I think I might skip this, but this is just reinforcing the state machine that that we go through when we're loading and openSSL and processing different sections that are at play. But yes, if there is a bug at one, suddenly the memory map can kind of get a little messy with attacker-controlled data. So we're going to start this going in some background now about ELF, since this is called ELFbac. What ELF does naturally is it divides text and data and metadata for loading into different sections. And so there's two views of the file. The static compilation view, which understands each section separately, and the runtime view, where it actually it forgets about these separate sections and just knows that this group of data are actually executable. These are read-only, these are read-writes. And the ELF is what demarcates these sections. And there is sort of a purpose to, well, this is executable. You know that there's some code in there. And what lies behind these ELF sections really is kind of interesting, and we tend to lose this information where we might have 3 separate C files that we compile into object files. In the end, they kind of they're still separated, but they're in. We can actually, with the right tools, keep those separate just as different pieces of policy, but still have them all be loaded. And actually, explicitly adding a piece of code or piece of data into a different section is fairly simple. And there's some, you set an attribute section, and then you give a section name, and this is in C, and that will tell the compiler to put it in its own section and name it so that for our purposes, you can apply policy to it. And now Prashant will take over.
Yep, so we heard from Bex about what ELF is and a little bit about the background. So now let's look at how ELFbac is, how we can actually write a policy for Spectre and what Spectre variant 1 was. So in Spectre variant 1, basically a malicious actor can influence the control flow of the program. So if you look at the code section, code example over there, like there is an untrusted offset which is being accepted from the input or from, it's being accepted from an input, and there is an if condition, and that particular check has to happen. The code inside the if section is obviously supposed to execute only when the condition is satisfied. But what happens is that when so some processors, not some processors, almost all processors do this speculative execution over here, where it predicts that there is a chance of that particular offset being lesser than the limit, and it actually runs the code that is inside it, and hence it puts the data that is inside the section, puts the data that is being read into the cache. So what happens over here is that the victim function can, it loads the secrets from the privileged memory, and that particular memory gets loaded into the cache. So why is it really challenging to mitigate this particular Spectre variant 1? So if you look at this, this is the proposal on LLVM in the Clang compiler. So their technique over here was to, so if you see over here, there is a condition, and then within the condition they use a ternary if condition again. So their whole thing was that if the speculative execution branch is happening, then you force the condition to be checked again. So why would you run it again? It makes no sense. And GRSec decided to run their own thing where they are using static analysis to figure out where this speculative execution happens, and then mitigate them by using elfenses. And that is what even Microsoft does with QSpectre, where they figure out using static analysis where this particular speculative execution bounds check bypass can occur, and then they introduce an elfence instruction over there to like mitigate this particular variant. So how about Linux? First, Linus Torvalds, he looked at the bunch of patches and he was like, it's not that it's a nasty hack. It's much worse than that. And then he was like, Intel is not serious about this, and Intel doesn't really want to patch this. But then how did they eventually go about it? This was the first patch. So it was again an ASML fence, and it was the exact same thing as what Microsoft wanted to do. And then they came up with another patch which was supposed to fix the previous one, where again they were like array index no spec, which is like saying that this particular array, there cannot be any speculative execution on this one. It is again a hack, as you can see. Like you really need some other technique to figure out where you need to initialize your arrays this way. It's not a holistic patch. You still need some sort of static analysis or some other technique to figure out where this has to be added. So yes, people are approaching it with a line-by-line process or by static analysis, and there are some other techniques that you need to use to like figure out where the problematic locations are, and that's where ELFbac comes in. Like we are giving the power back to the programmer or the developer, and we are helping them enforce their intent with respect to the data and the code sections in the program. Okay, so let us apply ELFbac to the variant 1 proof of concept. So if you look at the data in the program, the data that gets leaked, it is like this particular secret string. It's always so in the proof of concept they have a secret string, and we are mainly interested in that one string that gets leaked in the cache. And so we put it in a separate section using the attribute method in the ELF ABI. So we put it in a separate section, and this is the syntax that we use. And we also like put the different methods in the program in separate sections. So as I said, like you want to specify, you want to separate like the code and the data in separate sections. So we have two methods in our code, and we put them in separate sections. And then like, so this is the state machine that we were using. So of course, like in the original proof of concept, this is the sequence of operations that happen, but they weren't really enforcing it with a state machine. So we have two different states, the init and the go. So in the init state, the secret has to be, so the secret is a global. So of course, like in the beginning of your program, it has to, so your program, when the program initializes, it has to be able to read and write to this memory location, or else your program will segfault right over there. So like in the beginning of your program, you want to give read-write access to this particular global, and then as soon as the initialization happens, you don't want your program to like be able to access this particular memory location. So as you can see in our policy, like we have read-write access to the secret in the beginning, and then we revoke it, and we only have like executable access to the particular function that executes right after it. So this is our tool, which is called Mithril. So Mithril helps us like programmatically represent this particular state machine. This is written in the this is written as a Ruby DSL, or domain specific language. And what it does is that it converts this particular state machine that is represented over here into code, and it puts that in a separate section in your ELF binary, in this section called the .ELFbac section, and this section gets loaded by the kernel when the program is loaded. So how does ELFbac really mitigate Spectre variant 1? So since sensitive data and code is like put in separate sections, and the periods of execution that are less trusted are like are not given access to the sensitive data, and like parsing and modules of code that access libraries, they are only given access to data that it really needs to access. So we can write a policy that only writes to what we trust, and only writes only the libraries that we trust can actually write, and all this is actually enforced by the hardware. So why does this work? So the page table permissions are set by the ELFbac policy, and the processor respects these page table permissions that are set by ELFbac, and the speculative execution branch like fails to load the secret, and the TLB and the caches are flushed during state transition. So whenever there's a state transition, we flush the TLB and the caches because we don't want the data from the previous state to be accessible in the next one. And of course, there is no timing leakage, and the side channel is also mitigated because of the permissions that are set. Okay, so conclusions. ABI level memory objects are the sweet spot, as Bex described earlier. The benefit of using ELFbac is not just a Spectre mitigation. As we were describing earlier, it's more of a holistic solution where it mitigates a wide range of intra-process memory attacks. And the policy can be modified if you're adding additional libraries to your program later on, or if you want to isolate these libraries, or if you want to address newfound bugs. There is a performance hit, of course, because like we are doing TLB flushes, and we are also forcing state transitions and page faults. So of course there is a performance hit, and we are working on improving that. And the policy crafting tool that we described, Mithril, it needs some improvement, and we are like trying to build a test framework to query and test these policies that are crafted. So yeah, I guess we can take questions now.
Well, we didn't ask questions. We have stuff to give away. So I just thought of one. Wait. What type of cat are these? No?
There is someone.
Okay, that's too
Yeah,
hard.
there is someone.
Oh, yeah, sorry. Well, they're Russian or Mongolian. Maybe it has a similar name, or maybe it's a different name that I know, perhaps. But we'll give it to you. Manuel is how I know them. The leader of our lab, or former leader, calls them the privacy cats because they hate being tracked. And they can't be domesticated. They have a really poor immune system. So if they're in captivity, they kind of die from sickness. We have 3 more things to give away, unless someone wants to ask a question, and we can give you something for asking a question.
Yes.
Yes. That is interesting. I think you would want a little user input to say these are like the crown jewel data that we don't want leaked. And then you can probably have some static analysis that generates a policy that works with that. We have played with some generic policies that enforce loader actions. So there's a lot of processing that happens when the runtime loader brings a binary into memory. And a lot of interesting tricks can be done with the metadata in the ELF to get it to do random things, such as, well, I built a compiler that compiles a Turing-complete language into ELF metadata, and it's because it can happen, or like this Turing completeness happens and arises because the metadata don't respect their intent. And so we wrote a policy that will work on well-generated, like well-intended generated ELF files during loading, but would prevent the Turing-complete weird machine that arises out of these metadata. So that would be like a basic policy you can add to everything for loading. But for general, like the idea is it's up to the developers or to people who know the software to be like, these are special, and these are special phases or untrusted phases, and then put together something with that. So you have like a coarse-grained basic policy that helps at some level. Oh, you get a prize. Other questions? I'm not even looking. No other questions?
Yeah, there's one.
Oh. It's hard to really have to really compare the performance hit because it's really dependent on the number of state changes that we have. So I think there was some defaults, like the loading policy is what they measured and timed it for across all binaries in Ubuntu. And it was really because of the state changes.
Yeah, so like if you have a program that only that does like an SSH handshake in the beginning and then does something that's completely trusted, then like the first key read only happens in the beginning once. So in that case, you will not see that much of a performance hit. But if it's something where like it keeps switching to an untrusted state really often, like it keeps accepting user input or network traffic, so where you need to like parse the network traffic again and again, and you want to put the parsing in like a separate state, in that case, it becomes a bit more complicated, and there will be some there may not be 5x performance hit, but there will be a performance hit.
Yeah, there are
hardware
tricks that we're not using that people who actually know how to work this kind of thing and care do know and would tell us to use. So we can do better, but we don't at the moment. Do you want another prize? We need another question then, or we can ask one. Oh, great. There's some examples. So ELFbac.org has some pointers to a couple repositories. One is the x86 implementation, and another is an ARM implementation. And one day we'll merge the two, but they have examples like ping pong, where it enforces ping and pong. I don't know, and one that enforces something with libc that prevents libc from accessing anything in the main executable.
So the easiest example in the repository is ping pong, where you just have two different methods, ping and pong, and one variable, and you want to like restrict access to that particular variable from ping, but pong has access to it, and so on. So like that is the easiest example there is, but there are more complicated ones, as she said, like libc and so on.
Yeah, I mean, and we need some better tools to get like libc is a little finicky because it depends on the build of libc. Sometimes it has some interesting tricks it does. So like this is a problem with our tools to have like better support for these weird tricks that libc does and the loader does. But that's future work.
For this particular project, like we use the x86 version of ELFbac and not the ARM version.
Yeah. Well, we don't have the right hardware to test the ARM Spectre v1 proof of concept because we're poor academics. Or at least I was. Now I work in industry. Any other questions? If you don't ask one, I'll ask one.
Go for it.
Okay. The state motto or saying for New Hampshire, it was alluded to earlier. Oh, you were the first. Okay. Oh yeah, you already have one. You in the purple shirt, I think you were second. Yes, live free or die. Cool, that was our last. So if anyone else thinks of a question, we can still answer. Feel free to trade prizes. All right, well, thanks for coming. I'm sure you want to get ready for the after party.
Thank you, bye-bye.